In this video, we'll talk about how the systems method for using variation of parameters relates to the second order equation approach that we discussed previously. So when we did the second order approach to variation of parameters a while ago, it seemed like those formulas were kind of involved and crazy and came out of nowhere for how you get to the answer. What I want to do here is draw the connection between what we've done for that in the past and what we've just done here for solving systems by variation of parameters. So let's take a second order equation and see what that looks like converted to a system, and then apply our new method to that system. So we'll start with the generic second order equation. Say y double prime plus some p of t y prime plus some q of t y equals g of t. Now, if these aren't constants, we really don't know how to solve it, but we'll assume that we know how to solve it, and they're going to build the variation of parameters part out of it. So we have this, and we'll assume that we have a general solution to the homogeneous problem as c1 y1 of t plus c2 y2 of t. So let's convert this now into a system. So since we have a second order equation, we'll need two components. We need an x1 and an x2, where x1 is going to be y, x2 is y prime. And our equations will tell us that x1 prime is x2 because it's y prime. And then x2 prime is y double prime, which I can write in terms of this equation here to give me that x2 prime will be g of t minus p of t y prime minus q of t y, or g of t minus p of t x2 minus q of t x1. So we can write this in system form: x1 x2 prime, or vector x prime, equals x2 and this expression here, which I can then break down as 0, 1 minus q of t minus p of t times vector x, and then plus the vectors 0 and g of t. So in the context of our system, this here is the matrix A, and this here is the vector function f that we're going to use to do variation of parameters. But we have a head start here because we know a solution, or the general solution, to this problem. Because this came from a system where we had a solution, we know that this y of t will also solve the system if written in the appropriate context. Because y is x1 and x2 is just y prime, we know the general solution here is going to look something like c1 times y1 prime plus c2 y2 prime. Because this first component is just y, it's the exact same as it was before, and this one's just its derivative, because that's how this process is set up. Now, to use variation of parameters, I need the fundamental matrix, and that just comes from putting these two solutions side by side. My fundamental matrix x of t here is going to be just y1 over y1 prime here, and then y2 and y2 prime over here. We're going to need to find x inverse to work this out, so I better determine this is invertible. So I find its determinant, and its determinant is going to be exactly y1 times y2 prime minus y2 times y1 prime. This is exactly the Wronskian that we had defined earlier on for these solutions. So because we knew we had a general solution in the first place, that means these are linearly independent, so their Wronskian is non-zero, which means this matrix is invertible. So then we want to work out our solution using this. So the point is, for this variation of parameters, we have that capital X times this vector u prime is going to equal our function f. So u prime should be x inverse times f, which in our case will look like 1 over the determinant times this matrix, which is going to come from the inverse of f. So we're going to swap the on diagonal and negate the off diagonal, times f, and f here is 0 and g of t, because that's how this non-homogeneous part came into the solution, was at 0 and g of t. Now we can work out this product here and get that the vector u prime should be negative y2 times g of t divided by the Rankine or the determinant. And the second component is going to be y1 times g of t over the same denominator. Then defined u1 and u2, I would integrate these and multiply them by y1 and y2 respectively. And these are exactly the same formulas that we got for the second order method. Which means I would then get to write my general solution to the non-homogeneous part as y1 of t times a u1. u1 is the integral of this first component, plus y2 of t times u2, which is the integral of the second component, which is the exact thing we had in a previous chapter for the second order equation method. So really, the second order equation method for variation of parameters is just a consequence of what we do here in systems. And so in most contexts, particularly beyond second order or beyond two equations, the right way to consider that is in the matrix context, because then you're just taking the inverse of a matrix to solve it out. And you'll notice here, we didn't have to add any weird conditions like the one we had before for like u1 prime y1 plus u2 prime y2 equaling 0, like we had before. We didn't need that. That particular component here becomes somewhat irrelevant because of the extra 0 that we've added in this top row here. It's not exactly that, but it's related to that fact. But it's there. The point is we don't need extra condition, and we still get the same exact formula we got out before for the second order equation method, just using matrices and this more direct approach to it. That's the connection between those methods. They're really the same thing, and sort of the more generic and more applicable way to think about it is in the matrix context to make sure you get the right result for these non-homogeneous systems.